video. We're just going through the chapter 13, where we have been teaching you the stability analysis from chapter 13. I'm just taking the part of the examples. Okay, this was the example where we use the to find the roots of the equation. You can see. Okay, so this we got the roots of equation, and both of them are negative, so their system is stable. The one we've seen in the PowerPoint slides. Use the valve stability analysis, you can see in your slides, and also the theorems of Ralph's test in the slides, basically from this book. And this was the equation that we use to show the concept of the valve analysis. Okay, and we can see that what we've seen in the slides before, that all of them are positive. So the system, there's no change in sign, or positive no change, so the roots have no roots have positive real roots on the imaginary on the complex plane, and so the system is stable. Just a note here, we look in the from the book, the algebraic method for determining stability is limited in its usefulness in that all we can learn is stability. Okay, it does not give you how stable it is, or how close it is to the imaginary axis. You just know it's stable, and how many roots have made it stable, how many roots have made it not stable, but how much stability there is, I mean how close it is to the imaginary axis, we do not know. We have to solve the roots for that purpose. Okay, this one is an example where we have also seen in the class, where tau 1 equals to 1, tau 2 equals to half, and tau 3 equals to 1/3. This is the same as in the tutorial example. The same system. If we substitute the tau 1, tau 2, tau, you will get this as the characteristic equation, the 1 plus g, and we get the Ralph analysis here. We can get the Ralph analysis here. So we will then see what is this is in terms of Kc. The Kc is not given, so it's asking what is the Kc that will make it stable. So in this case, we will see that if you apply the Ralph analysis, you get these values in the first column, and the positive or negativeness will depend on the value of Kc. Okay, so if we put Kc, we go through this one. For the system to be basically stable, and Kc has to be less than 10. If it's less than 10, then everything will be positive. So system is stable only if Kc is less than 10. Okay, in the tutorial, the question will give you different values of Kc for you to check what values of Kc make it stable or unstable. So this is the value of the condition for it to be stable is that Kc has to be less than 10. Okay, this if you have MATLAB, you can check the roots of equations and you can solve, and you're going to get all this negative for the previous part that we have shown you before. If you have the MATLAB, if you do not have, then that's where we'll have take difficulties in getting the roots of the equation, and it will take time. But if you use the Ralph analysis, it's more simpler without having to solve the roots of the equation. Okay, in the case where Kc equals to 10 just now, the case there, then what will happen is that this is where we start to use theorem 3, is that the one of the rows will be all zeros, and to solve the value of the roots, where the roots are on the imaginary axis, which makes them 0, then you can use this equation. The theorem says you see s squared plus d, that what is the coefficient before that row n, which is n minus 1 row, so you value 6 and 66, and when you put this, you will solve. These are the roots of the equation that is on the imaginary axis, s plus or minus 11 square root of 11j. And we know that just now it was a third order polynomial equation, so there must be 3 roots. We've put into factor in this form. We already found 2 roots on the imaginary axis, so we can find the third root by solving this one. So we will find that the third root is s equals to minus 6. Okay, and the roots of the equation are therefore S equals to square root 11j, S2 minus square root 11j is a conjugate roots on the imaginary axis, and the other one is minus 6. So this one is a positive. This is the on the left hand side, stable. This is just stable, basically, as I said before, on the verge of stability. According to stability criteria, it's not stable, but in reality, it is just stable, just giving what response is it giving? It's giving a continuous oscillation. That means when something system giving continuous oscillation means it's just stable, on the verge of stability or instability, and that means the roots on the imaginary axis for that system. If you use MATLAB to solve, you get the same thing. Minus 6 and the 2 square root of 11, which is 3.3166i. So this is the other way we have MATLAB to solve the roots of the equation. Okay, if you look at the system now, the same system we've seen in the tutorial and in the book. If you put a PI controller, which we know the equation is KC1 plus QC into 1 plus 1 over tau is. If you put the values of PI, given case is 5 and tau I equals 0.25, you are going to get the characteristic equation in this form, 1 plus g, and you get in this polynomial. So you want to know the stability of the system. You get the Wealth array and put it into the coefficients into the Wealth array, and we come out with the figures. Okay, is there a negative sign or not? First of all, we use the Wealth array theorems, and then we check that is there any negative sign? Yes, there's negative sign, so which means the system is unstable. Because it shows some roots on the left, on the right hand side of the plane. And theorem 2 say how many roots? Check what is the change, how many change of sign. 1 to 6, there's no change of sign. 6 to 5, no change of sign. 5 to minus 108 is one sign change. Minus 108 to 120 is another sign change. So how many sign changes are there? There are 2 sign changes. Okay, because there are 2 sign changes, using theorem 2 means there are 2 roots on the positive real parts. Okay, what are the 2 roots? It doesn't tell us. You have to solve that, but at least you know that there are 2 roots on the positive real parts from theorem 2, and the system is unstable. Okay, so we can see that by putting the integral action, the system becomes unstable. But if you have just the KC5, just now we saw, or just the proportional controller, 10 is the limit, anything less than 10 is stable. But once you add the KC integral controller, it will make unstable depending on your tuning constant and so on. Okay, so this is the way of checking the stability and how many roots make it unstable. And this, you got MATLAB, you can also solve it, and you find the roots, 2 roots on the left hand side. What are the roots you can find? As I say, if you have the MATLAB tool, of course you can solve all these things straight. But if you do not have, you are doing it manually. The Wealth array, a very fast one method to check on stability and how many roots make it unstable. Okay, so then there's a summary of the chapter. We have given you 2 questions to do on this chapter. We'll go through that. One of them is this one, 13.1. It's the same system as you examples just now. It's the same system. When you get the characteristic equation, 1 plus g, will come out with the polynomial degree 3. Okay, and you will put in the Wealth array, then you will get the conditions for KC stability. So you try 9.5 stable or not, 11 stable or not, 12 stable or not. It's just similar question as given in the example in the book. The other questions, 13.9, we'll go to later. From that, you will be able to understand using Wealth stability analysis much clearer. Okay, thank you very much.